that was constant volume. We can also talk about heat evolved at constant pressure. So when a chemical reaction occurs that's open to the atmosphere, then the pressure will be constant. When that happens, the energy can evolve as both heat and work. Usually we're only interested in the heat exchanged, and we're not really interested in the work because it's not exactly productive work. And so we have another term here called enthalpy, and the enthalpy is the H. H of a system, enthalpy of a system is the sum of its internal energy and the product of its pressure and volume. So this looks a little bit like that Q plus W, doesn't it? Enthalpy is also a state function, meaning that how it gets from one state to another doesn't matter, it's just the difference. So enthalpy change is delta H. So delta H for a reaction is the heat evolved in a reaction at constant pressure. At constant pressure, we have delta H is equal to delta E plus P delta V. We did not put a delta in front of P because the pressure isn't changing. It's a constant pressure. We have said before that delta E was equal to Q plus W. Here we stuck a P in there to remind ourselves that this is at constant pressure. Q with a little v means at constant volume. It's Q plus W plus this. Well, this is negative W, isn't it? Negative W plus W, ta-da, they go away. It's very convenient. And so delta H ends up being equal to the heat at constant pressure. So this is a really useful idea. So delta H and delta E are very similar in concept, and they are often similar in value, but they are not the same thing. Delta E is a measure of all the energy, both heat and work, that is exchanged with the surroundings. Delta H is a measure only of heat exchanged under constant pressure. So most of the time the difference between them doesn't really matter. But it's biggest, the difference is biggest for reactions that produce or use large quantities of gas, because those sorts of reactions end up having large volume changes, and that can be a problem. That makes delta H and delta E be differenter? I don't know, I'm just struggling tonight. So delta H is a lot like delta E. So easy to get them mixed up. If delta H is positive, heat is being absorbed by the system. That's called an endothermic reaction. When delta H is negative, heat's being released in an exothermic reaction. So the signs for them are the same as we've been thinking about with delta E, and with Q. Chemical hot packs. Here's a picture of a cold pack. Okay, there's no picture from the top one. We'll just talk about it, and then that's probably why I put that on the bottom. So chemical hot packs that have iron filings in them get oxidized, and there's a transfer, a release of energy from the reaction, and it goes into the surroundings. If your hands are near the hot pack, they will get warmed up. We can also have chemical cold packs. They are an endothermic process. When we dissolve ammonium nitrate in water, it absorbs heat energy from the surroundings and it gets cold. We can also view exothermic reactions from a molecular standpoint. We're used to seeing things at what we often call a macroscopic level, something that you can see with your eyes. But it's very helpful to imagine zooming in down to the particulate level and looking at what the atoms and molecules are doing. An exothermic reaction gives off thermal energy, and that causes the temperature of the surroundings to rise. What's going on there? Bless you. Well, the extra thermal energy is coming from the conversion of some of the chemical potential energy in the reactants into kinetic energy in the form of heat. So we've got, in a reaction, we've got bonds being broken and new bonds being formed. If the bonds that are broken give off more energy, if the bonds that are broken require less energy to break than the bonds being formed give off, we've got an excess of energy. And so that energy has to go somewhere. In an exothermic reaction, the products are going to have less chemical potential energy than the reactants, and that difference in energy is released at heat. I hope I have a picture. No, there's no picture. Looking at an endothermic reaction, it's the opposite. The temperature of the surroundings drops because the reaction is absorbing some of the thermal energy from the surroundings. Existing bonds are being broken and new bonds are being made. It takes energy to break bonds, and when bonds are formed, it releases energy. So it's like you have to, like with an investment, a lot of times you have to put out a little bit of money before you can get a payback, right? Well, some of those investments don't work out very well and you end up losing money, and other ones you end up gaining money. And so endothermic, exothermic reactions kind of work that same way. For an endothermic reaction, it costs more to break the bonds than is released when the new bonds form. And the result is that some of the surrounding thermal energy gets stored as chemical potential energy in those products. So the energy is not appearing or disappearing, it's just moving in different forms. The temperature drop tells us it's lost kinetic energy of the particles, right? Temperature is a measure of the average kinetic energy of a substance. High temperature, particles are moving faster. They have more kinetic energy. So if you activate one of these instant cold packs and it sucks energy from the surroundings, it takes energy from those particles, causing them to slow down. They get colder. It's really a different way of thinking about hot and cold than what we encounter just in our everyday lives. So we've talked about heat of reaction. We also talk about enthalpy of reaction. So this is delta H for the reaction. It's enthalpy of reaction. We also call it heat of reaction, although it's different than that delta E. Enthalpy is an extensive property. It depends on the amount of stuff. Intensive properties are intrinsic. They don't depend on how much there is. But an extensive property depends on how much stuff there is. So the amount of heat transferred depends on how much reactants react. So by convention, when we do these sorts of equations, this is the equation for the combustion of propane, we'll list delta H for the reaction, and it'll just be listed with joules, kilojoules, calories, an energy unit, and it won't be per mole like we did in the previous example. By convention, we just have decided we're going to just list delta H for the molar amounts in this balanced chemical equation. And so this becomes a useful conversion factor for figuring out how much energy would be given off if you burned 5 moles of this. So we can say that 1 mole of propane is equal to 2,044 kilojoules of energy being given off. Or 5 moles of oxygen is equivalent to minus 2,044 kilojoules of energy being given off. Any questions? Let's look at an example. Ammonia reacts with oxygen. There's the reaction. We've got delta H for the reaction. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So this ends up being like a stoichiometry problem. We've got 155 grams of ammonia. And so we're going to go grams of ammonia. We always have to go to moles. We did calculations like this with E, right? Or am I thinking of a different class? Okay, that was my other class. What's the thing we chanted for stoichiometry? grams to moles to grams, right? Okay, that's Dora's path for success in chemistry. Grams to moles to grams. We're going to see that there's variations. We've already seen a variation with solution stoichiometry, right? We had volumes instead, and we had concentrations. And we did some things with moles or volumes of gases as well. This is another variation. Here, if we start with grams of ammonia and go to moles of ammonia, we can actually take a little shortcut and go directly to kilojoules. Because this guy relates to these molar amounts, and so we don't have to go moles of this to moles of something else. We can go directly from moles of anything to energy. And sometimes this little thing comes at the end, and sometimes it comes at the beginning. So we're going to go grams of ammonia to moles of ammonia directly to kilojoules of energy. So 155 grams of ammonia. Oh, I started doing ammonia. We're going to go to moles of ammonia, and we're going to use the molar mass of ammonia down there. And then we're going to use this number. This is minus 906 kilojoules per what? Per 4 moles of ammonia. See this right here? 4 moles of ammonia generate this much energy when they react. 155 divided by 17.034 times 906, negative number, divided by 4. And how many significant figures should this number have? Should have 3. The train says 3. 3. One more time? Yes. Okay. Yeah, I know. You can stop now. So how should I report that with 3 significant figures? Scientific notation would be the best. So 2.06 times 10 to the third kilojoules. Any questions? And that leads us to constant pressure calorimetry, which more closely matches what we did in lab. So we can measure delta H of reaction for many aqueous reactions just in literally coffee cups. Okay, 2 nested styrofoam cups. It's good to have some sort of a lid. Why would you want a lid on here? So the heat won't escape, right? And it says loose fitting. Why do we want a loose fitting lid? Because we want it to be constant pressure, right? We want it to be constant pressure so that we don't have any pressure building up. So then we can look at Q for the solution. So Q for the solution is the mass of the solution times the specific heat capacity for the solution times the change in temperature. We measure the change in temperature just using a thermometer sticking in there. So whatever the reaction does, whatever energy it releases, is going to go into the solution. And so we have this same relationship here. So the heat of reaction is equal to the Q at constant pressure, or the heat of reaction, the heat generated. And if we want to get delta H reaction per mole, we just divide by the number of moles. So here's an example that leaves no room for doing any work. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to the reaction. There it is. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.4 to 24.21 degrees Celsius. Calculate delta H for the reaction as written. Use 1 gram per milliliter as the density of the solution, and C equal to 4.18 joules per gram degree Celsius as the specific heat capacity. That's a lot of words. Let's draw a picture. This is the sort of picture that I can handle. I can draw coffee cups. Isn't that nice? This is a coffee cup. And so in the coffee cup, we have some water. And we measured the temperature change for the water, delta T for the water is going to be the final minus the initial temperature, right? 24.21 minus 23.40. So the change in temperature is 0.81 degrees Celsius. Did they give us the mass of the water? Because we're thinking we're going to need to do some Q equals MC delta T thing, right? And we don't know what the mass is. So let's think a little bit more about what did we put into the calorimeter? Well, we put 50 milliliters of 0.1 molar silver nitrate. I'm going to skip the zeros there because I'm just labeling. I'm not calculating right now. And we put 50 milliliters of 0.1 molar HCl, right? What's the total volume of liquid in the calorimeter? 100 milliliters. Could we figure out the mass of that? Yeah. So we need to use the density. They told us what to use for the density. They said use a density of 1.00 grams per milliliter. And so we end up with mass is equal to 100 grams, right? So now we have the mass and we have the change in temperature, and they told us right here what the specific heat capacity is. So we can calculate the energy Q absorbed by the solution by the calorimeter. And that will be equal but opposite in sign to the heat given off, Q given off by the reaction. So Q is going to equal the mass times the specific heat capacity, joules per gram degrees Celsius, times the change in temperature. Three, 8. Thank you. And that will be joules. How many sig figs does that result have? 2, because of this temperature. Oftentimes it's the temperature that limits it because we have a small temperature change there. So even though we used a really nice thermometer that gave us 2 decimal places, the change was less than 1 degree. So it's only got 2 sig figs. So that's Q. Which Q is that? Is that for the calorimeter or for the reaction? That's for the calorimeter, right? Q for the reaction is going to be minus 338. Right? Because it gave off energy. The calorimeter absorbed energy. And this is wanting us to find the heat of reaction, delta H, for this reaction as written. Okay, I'm going to do some erasing because I need a little space here. Well, we need to divide by the number of moles, right? Because we want for this reaction, we want for 1 mole of this or for 1 mole of that. Do we know the number of moles that were added? The last example we did, they gave us a mass, right? This example, they didn't give us a mass that we can convert to moles. Did they give us a way to find the moles? Yeah, they gave us a concentration and a volume, right? So let's use a different color here because we're doing a different part. We've got 50 milliliters, which is 0.0500 liters of 0.100 moles per liter of silver nitrate. So that ends up being 0.00500, right? Moles. Everybody okay with that? How many moles of HCl? We don't actually need to calculate it, do we? It's the same. It's the same volume and the same concentration. It's going to end up being the same number of moles. We need 1 mole of this for every 1 mole of that. So this is a stoichiometric situation. We've got equal numbers of moles, and we're supposed to have equal numbers of moles. So then it really doesn't matter which one of these we look at. They could be mean and have given one of these that was different, and then we might have a problem. So this is the number of moles. So we need to take our Q down here and divide it by 0.005 moles. So we've got minus 338.58 kilojoules divided by 0.00500 moles. Negative 67716 kilojoules. And that would have 2 significant figures. So we would call that 6.8 times 10 to the 4th kilojoules. Delta H RXN equals minus 6.8 times 10 to the 4th kilojoules. Any questions? Yes? Oh, that's an awesome question. I did that to trick you. No, actually, I don't know where I got that from. No, that was just a flat-out mistake. Thank you for asking about that, because that's just wrong. Okay, so it's just joules. I can fix it. It's joules. Okay, and so then that's joules. And so how about here. Come on, erase. Let's convert that to kilojoules. I don't know where these things come from. So converting to kilojoules, we would divide by 1,000, right? So we'd put the decimal point here, and we'd end up with minus 68 joules. I thought this looked like an awfully large number. Oh yeah, that's, okay. Let's just start that one over. Minus 68 joules. No. The part of the problem is I can only see a little part of the screen that I'm writing on, and so I think I need to get a bigger iPad. Okay, any other questions?
Is that joules per mole then?
When we report delta H reaction for the equation, it's for the equation as written. Now, if this had had a 2 in front of it, we would have had to multiply delta H by 2 so that it would apply to the equation. And it's saying for the reaction as written. Okay, that's a good question. Any other questions?